Hello. Okay, today we're going to learn something about electric motors. Electric motors, as a mechanical engineer, are going to be one of the most important actuation devices, I believe, that you're going to get involved in. Maybe some hydraulics, but electric motors are going to be important. So, unfortunately, we have to learn something about electricity. So today, first of all, let's just look at what the element laws are. Element laws for electricity. And so the only one that I ever can remember, V equals IR. So that's an easy one. We know that one. We also know that voltage is equal to L, the inductance, and then we have to change the current, DI dt. So the next is going to be, we're going to say I is equal to C dV dt. Today we're not going to use that one, but just as a matter of completeness, I'm going to put that in here anyway. So what we are going to look at is we're going to look at an electric motor. Now, I always kind of joke that electric motors, typically, an electric motor has a red wire and a black wire. I don't have black here. You wouldn't be able to see black, so we're going to have a black wire. And typically what we're going to do is we're going to say, okay, so out of the red wire, there's some kind of a resistance on the motor. So when you wind up all of the coils on a motor, there is some overall resistance. And because you're winding the coils on a resistance, there is also some kind of an inductance. Now, I draw my motors looking this way. That's because I'm an old guy and they used to have brushes on the motors. And so this is ground, but we can also take that back over to the black wire. So we have two wires that go off. Now the motor, generally speaking, the motor is going to drive some kind of a shaft. There may be some kind of a rotor on the motor. Oftentimes there's a gear on the motor. There's a larger gear with an output shaft. And so here's the output shaft. And oftentimes what I'll do is I like to put some kind of a disturbance on the output shaft. So you can grab a hold of the output shaft. I'm trying to get my disturbance. I may have to change this disturbance direction, so I'm going to put the output shaft in that direction. So what we'll do is we're going to look at the current flowing through I. And then what we'll do is we're going to look at the voltage drops across each element of the motor. So there's going to be a voltage drop that's going to be V equals I R sub M. So that's one voltage drop that's going to happen. We're going to have a voltage drop that's going to be equal to V equals L di dt. That's going to be a voltage drop. And then it turns out there's one more voltage drop that is the V sub EMF, the back EMF voltage drop. So motors work in two ways. If you put a current into the motor, it makes the motor move. And if you move the motor by hand, it generates a current. And so that current is the back EMF. And so what we can say is that the back EMF, there's a motor constant called the motor EMF constant, and that voltage that's across the motor is proportional to the velocity of the motor. So we're going to write it that way. And so now we've got all the electrical parts of the equation. So what we can say is that if this is V in, if this is the input voltage to your motor, then we can sum up the voltages across the motor and set those equal to V in. So we're going to say V in is equal to I R sub M plus I R sub M plus L di dt. That's one way. And then we're going to add that is also plus Ke times theta dot. So those are what. So now we've summed up the voltages along that motor circuit. Now, what we're going to do, in the end, we're going to want a transfer function. So as soon as we say transfer function, we're going to just go ahead and assume that all the ICs are equal to 0. And we're going to take the Laplace transform of this equation. So I'm just going to say V in is equal to I R plus L I S plus K E. That's theta M S. So that's theta of the motor. Now let me just make sure that we define our datums here. I'm going to get some different colors and see if those come out very well. So what I'm going to do is I'm going to say that this is plus theta M. So the motor goes in that direction. And so what I can see is if the motor goes in that direction, then this output gear, it's going to go in the opposite direction. So this is plus theta out. So that's the output direction. And good thing I chose the direction of the disturbance in the right sense. And what I'm basically doing is I always like to say, well, the motor, if you grab a hold of it and put a load on the motor shaft, it's going to tend, the positive direction of that load is going to tend to move the motor in the positive direction. I think we can just leave this way for now. So here is the electrical equation that governs the motion, that governs the electrical operation of our motor. We might want to draw, so always in our cases, right, so free body diagrams of the motor rotor. So we might want to draw a free body diagram of the motor rotor. And so what I'm going to do is I'm going to draw the rotor again. Here's the rotor. And I'm going to go ahead and put this shaft on the output, and I'm going to put an output gear on the shaft. It's very similar to what we've done. Now, let's see. I've already defined the datum for this thing. This is going to be plus theta m. And if I want to make sure that I'm including all of the dynamic forces, then the very first thing that I want to do is I want to put a J of the motor theta double dot m. So the motor has some inertia. It's small because it's just that little round thing that spins around, but there's some inertia there. I'm also going to, just for the heck of it, I'm just going to include a B theta dot m on the motor, because I'm going to say, well, somebody put some kind of I don't know, WD-40 on the shafts of the motor, and that gives you that there's some kind of damping on the motor shaft somewhere along the line. So it could be very low, and later we can put that to 0, but for now I'm going to include that in. Finally, there's one more force that I'd like to put on here, and that is the force on the gear. I'm going to call that the interaction force, F sub I. And then I'm also going to make sure that we know that this gear is of radius 1. So we're going to call that gear radius 1. All the dynamic forces onto this rotor, and now what I'm going to do is I'm going to sum the moments around the rotational axis of the motor. So that's going to be J M theta double dot m plus b m theta dot m plus f sub I r1. I left off one last force. So from our electrical equations of motion, what we're also going to look at is we're going to say that the torque on the motor is equal to the motor torque constant times the current. And so I'm going to draw that motor torque constant in a direction that tends to make that, here's tau of m. So that tends to make my motor go in a positive theta m direction. So I'd forgotten that, so let's make sure we do that. Now we'll notice that that is also tau m. That equals km times I of the motor. So we've got it all there. So we've got all our little parts there. And so now we would also, let's also then now draw a free body diagram of the output gear. Outpug. I don't have a pug. Oh no. All right, I'll try and erase that. Output. I just misspelled output here. Output gear. Okay, so here's the free body diagram of the output gear. I'm gonna make that free body diagram look this way. Okay. So what I'm going to do is I'm going to apply an equal and opposite reaction. This is going to be F sub I, right? So the F sub I works on the tooth of that output gear. I've got the output gear. Now if I say that the output gear also has some thickness, I could call it a thin disc, and we could find out what the output inertia is for that. And then, as I said, one of the things that I've got on here is I've got a disturbance force on the output shaft, D, and we've also already defined what the direction of positive theta out is. We've already defined that. And so now what we can do, before we forget, this is a dynamic systems course, so let's go ahead and put, this is J of the output gear. So notice that this J for the output gear, it could just include the thin disc. But if you're making like a robot leg out of it, you might also have some kind of a big bar on here, and we'd use that output inertia to include whatever inertia might happen to be on here. So this is J out, theta out, double dot. And then we're going to have another force on here that this is going to be B sub out, B sub out. So maybe there's also bearings on the output shaft that have some kind of viscous damping. Perhaps this is the wind turbine blade and there's some kind of aerodynamic viscous damping. And what we're going to say is that that damping is mostly dependent on the velocity at the output shaft. So now we've got all of our parts on here, and we can sum up the moments again about the axis, and we're going to do it this way. J out, theta out, double dot, plus B out, theta dot out. Let's see, I'm going to go ahead and define this to be R2. That's going to be R2. And then what I'm going to do is I'm going to set that equal to F sub I times R2. So that's the moment around that, plus D. All right. So now we've got our equations for the motor rotor. We've got an equation for the output gear. And now what we're going to do is I'd like to combine those two things. And what we're going to do is let's go ahead and let's write this equation, and we're going to plug in for V sub I here. So this is going to be theta J M theta double dot M plus B M theta dot M, piece of fuzz there, plus, so let's like R1 times F sub I. So I can just see what F sub I here is going to be J theta out, theta double dot out, plus B out, theta dot out, minus D over R1. And that's going to equal Km times I. So here's our equation. We maybe do a little bit of cleanup on this equation. And we might write it this way. Jm. So let's see, what is theta double dot M? Theta double dot M is going to be R2 over R1 theta double dot out. And then this is going to be plus J out theta double dot out times R1 over R2, that should be a 2, over R2, oops, over R2, theta 1 over R2. Okay, here, let me just see if I can straighten that up real quick. Okay, R1 over R2. So that's going to be the, and then we're going to have, so this time this is B out plus BM R1 over R2 times theta double dot out is equal to Km times I plus D. And D is R1 over R2. Sorry, that's not, I'm squeezing over to the end. I'm going to come back over here. So now let's come back over to this side, and let me just go ahead and write that entire equation. So what we've done is we've got the electrical equation of motion. We've done a free body diagram for the rotor. We've done a free body diagram for the output disc. We've got an equation for that. We've combined the two mechanical equations in a way. And so now what I'm going to do is I'm also going to combine those this way. It's going to be J0 plus Jm. And you know, what I'm going to do is I'm going to multiply by R2 over R1. So I'm going to multiply this whole thing by R2 over R1. The reason I'm going to do that is that what I see is that I've got the variables here, and I've got the output. So here, this is Km times I. This is the torque at the motor rotor, and this is the disturbance, but it's also at the motor rotor. I'd like to see what it is at the output shaft. And so I'm going to multiply the whole thing by R2 over R1. When I do that, what I can see is that the Jm goes by R2 over R1 squared. That's going to be theta double dot out plus, now I'm going to have B out plus BM R2 over R1 squared, and that whole thing is going to be times theta dot out, and that's going to equal KM I R2 over R1 plus D. So now we've got the entire equation. Here's the mechanical equation of motion for this system. Sorry, there's a lot on this board, but I don't manage my board space very clearly. Okay? So once again, electrical equation of motion. That's the electrical electrical equation of motion. So that's the electrical equation of motion. Here's the mechanical equation of motion. If I have any more space, you know what? So there's a couple of substitutes that I can substitution. So I'm going to call this one B equivalent prime. So I'm calling that B equivalent prime. So what the equivalent damping at the output shaft is, it's whatever the damping is on the output shaft plus whatever the motor damping is, but that's times the gear ratio squared. Again, the output, I'm going to call this J equivalent. So this is the equivalent motor, the equivalent rotational inertia is the rotational inertia of the output. So that might just be this thin disc, but we might have something else on here, a robot leg or the wind turbine blades that you see out across the plains. And then what we're also looking at is part of the inertia is whatever's at the motor, and that's multiplied by the gear ratio squared. So I've got all those things. But you know what? So what I'd like to do, like I could take the Laplace transform of this pretty easily. I'm going to take the Laplace transform pretty easily. It's just going to be J equivalent S squared plus B equivalent S times theta is equal to R2 over R1 Km times I plus D. This is the one I'm going to work with from now on. So I'm going to go forward with this one. There we go. That's the equation of motion. Okay?